Alright, so good evening everyone. Let's start with the second week tutorial session. Before we begin, I would like to reintroduce myself. I am Srishi Sudhar. I am a PhD student associated with the Center for Systems and Control at IIT Bombay. And I'm also a TA for this course, State-Space Approach to Control System Analysis and Design. So let's begin with the second tutorial session. Alright, let's begin. So let's begin by recalling the concepts that were taught in the second week session. So first one is to convert a state space model to its transfer function. Second one is to convert a given transfer function to a state space model. Since the state space representation is not unique, so we are going to focus on three forms. The first one is the first companion form. Also known as the controllable canonical form. Second companion form, or the observable canonical form. And the third one is the Jordan form. Right. So in addition to this, we're also going to discuss transformations between state space models. Finally, we'll discuss state equivalence. State equivalence. All right, so let's begin. First topic is conversion of state space representation. Transfer function. We say that the state space is given by x dot equals ax plus b and y equals cx plus d. So given the matrices A, B, C, and D, the transfer function transfer function is given by C Si minus A inverse times B plus D. So S, because we are talking about Laplace transform. Alright, let's look at an example of a second order system. So derive the transfer function g of s for the following state space models. First part is x dot equals 0, 1, x plus 1, 0 times c. And then y is 1, 0, x. So first let's observe that in this question d is 0 and this. Alright, so what's si minus a? So this is s 0, 0, s minus 0, 1, minus 2, minus 3. This is s minus 1, 2, and s plus 3. Since it's a second order system and we have a 2 by 2 system matrix, so it's easy to compute its inverse, right? So for any matrix A, like A1, A2, A3, and A4, the inverse is given by 1 upon determinant of A. Then we swap the entries on the main diagonal. This becomes A4, A1, and multiply by minus 1 on the octet variables. Alright, so this is applying this rule. We have Si minus A inverse is 1 upon S plus 3 plus 2. Then we have S plus 3 S and 1 minus 2. Okay, so this is given by so C times Si minus A inverse is C is 1, 0. Alright, so this is 1 by 2 and 2 by 2. This is S plus 3 and 1. C times Si minus A inverse B is B is 1, 0. So it is simply S plus 3 over S square plus 3s plus 2. So this is the transfer function of the system. So observe that we have a second degree polynomial in the denominator. We also have a second order system because the matrix A is of size 2 by 2. Correct. Let me know if you have any doubts. Let's move on to the next example. Part 1. I'm just going to write down the matrices directly. So A is minus 2, 1, 1 minus 2. B is 1, 1. C is 0, 1. And D is 0. Okay, so let's quickly compute Si minus A, which is going to be S plus 2 minus 1, S plus 2 minus 1. And its inverse is so S plus 2 squared minus 1, S plus 2, S plus 2, and then 1. So this becomes S plus 3, S plus 1. Alright, so C times Si minus A inverse is S plus 3, S plus 1 times 0, 1. Alright, so this becomes 1 and S plus 2. Let me know if there is an error in the calculations. So this is C times Si minus A inverse with 1 S plus 2 and B is 1, 1. This is simply S plus 3 over S plus 3, S plus 1. So this term gets cancelled and here 1 over S plus 1. So what can we observe? That we started with a second order system, but the transfer function, but the degree of polynomial in the denominator is of 1, right? So the system is of first order. And then we have the sign of A as 2 by 3. Okay. So this means that there might be a state so that you can write, let's say that state is Y, so that you can just write Y dot equals AY plus B, where A and B are scalars. And this Y may be a linear combination x1 and x2. And you can have the output, let's say the output was C times Y. Let's look at the second part of this question. We again have the ABCD matrices. A is -1, 0, 0, -3. B is 1, 1. And C is 1, 0. So I think A and C are different as compared to part 1. Yes. Now let's compute the transfer function. So Si minus A is S plus 1, S plus 3, 0, 0. So in this case, Si minus A inverse is simple. So this is will be 1 upon S plus 1, S plus 3. Right? And let's multiply it by pre-multiply by C. So C times is 1, 0. S plus 3, 0. 0 and S plus 1. And we have S plus 3 and 0. Then let's post multiply by B. Once which is 1 upon S plus 1, S plus 3, 1 times 1, 1. This is again S plus 3 over S plus 1, S plus 3. So you can see that we have the same transfer function as in part 1, even though the state space matrices were different, right? So let's see. 1 and 2 have the same transfer function. This implies that the system under consideration is the same. And note again that the state space model is not unique. The state space representation of a system is not unique. As you have just seen that we have two different state space representation of the same function, of the same transfer function. Now let's consider a third order system so that we can see how to compute Si minus A inverse in a regular system. This is question 3. Determine the transfer function following system. So it's defined by the matrix A, B, and C. So I'll write down these matrices. 0, 1, 0, 0, 0, 1, -6, -11, -6. Input is present in the differential equation of the last state, and C is a linear combination of all the three states. Okay. So we still want Si minus A inverse, right? So Si minus A is add the diagonal entries first. S and S plus 6. And then the other entries are simply -1, 0, -1, 0, 6, and 11. Okay. Now to compute Si minus A inverse, we can use its cofactors and adjoint matrix, right? So first of all, the determinant is S times x squared plus 6s plus 11 and plus 1 times 6. Uh, is it -6 or plus 6? Let me know if it's incorrect. I have x cubed plus 6s squared plus 11s plus 6. Alright, now let's compute the cofactor matrix of A. And this is computed. So for each of the entries of the matrix Si minus A, we have -1 to the power I plus j and its corresponding determinant, right? Instead of A is, I'll write the expression, I'll write down the matrix. You can just verify this later. X squared plus 6s plus 11 minus 6 and s squared. Alright, so after this, we'll compute the adjoint of the matrix. So adjoint of, sorry, this is cofactor of Si minus A. Okay, can you hear me? Just confirm if you can hear me and if the screen is visible. Right, let's resume then. This is cofactor of Si minus A, and the adjoint of Si minus A is the transpose of this cofactor matrix. So cofactor of Si minus A transpose. And Si minus A inverse is then simply 1 upon determinant of Si minus A times adjoint of Si minus A. So you can compute this. I will write down the expression for GS. So GS is going to be 1 upon determinant of Si minus A, this is 6 squared plus 11 is plus 6 times C, which is 451 times this adjoint of the matrix times B. Okay, so this becomes S squared plus 5s plus 4 upon S cubed plus 6s squared plus 11s plus 6. So you can verify the calculations there. Alright. So let's move on to the next topic. This is conversion of transfer function. Plate space form. Alright, so let's recall a few reasons for doing so, and then we'll move on to questions. So reasons for converting transfer functions to state space models. The first one is because control system design or the modern control system design techniques based on state space models which you convert the differential equation of a system to its first order form, right? And the next one is that algorithms require first order differential equations for simulations and validation of control laws. Alright. So what are the problems on conversion of a transfer function to state space form? So let's see. Given a transfer function, is it possible to convert to the state space model? Is the state space model right? Because I've just seen a question in which there were two different state space models and we had the same transfer function. We know, and of course we have the three forms, which is the first companion form, the second one, and the Jordan. known as controllable canonical form, observable canonical form, and the Jordan form. And how do we obtain canonical forms? So let's say that we have a transfer function y is over u of s. So we'll consider third order systems. The numerator is b3s3 plus b2s square plus v1s plus v0 on s cube plus a2s square plus a1s plus a0. So this is the standard form which we use to obtain the canonical state space models. And standard form has 1 and the highest degree of the as the coefficient of the highest degree in the denominator. Alright. And now we want to obtain the state space model x dot equals ax plus b. So we need to find out a and b based on the coefficients b and a, right? Small b in terms of a and b matrices, a, b, c, and d actually. To b3 and a0 to a2. Right. So for the first combining form, so first ensure that the transfer function is in the standard form. If it is not, then convert it. For example, if there's a number here, you need to divide the numerator by this number so that we have s cubed in the denominator. Alright, once the transfer function is the standard form, you can directly write the first companion form for the state space model. And in that we have a equals 0, 1, 0, 0, 0, 1, then minus a0, minus a1, minus a2. Observe that the first two rows implies that we have a chain of integrators, right? The one shifts to the right. So for example, the first state is x1 dot equals x2. The second state is x2 dot equals x3. And the last state is a combination of the states. So this implies that we have a chain of integrators. Why? Because x1 is actually integral of x2, right? And so on. So this is A, and then B is simply 0, 0, 1. And C in this case is B0 minus B3A0. One minus B3A1. So observe that B3 is always there. And then finally we have B2 minus B3, B2. And D is always remember that for the first companion form, D is C. Now, in case that B3 is 0, it would simplify the expression for C, right? So B3 is 0 means that the transfer function looks like B2s square plus B1s plus B0 upon s cube plus a2s square plus a1s plus a0. So since the degree of the numerator is less than that of the denominator, this is a strictly proper transfer function. And for such strictly proper transfer function, C matrix is simply B0, B1, B2. Alright, so let's look at a question. G of s is 3s squared plus 7s plus 50 s cubed plus 7s squared plus 14s plus 8. Alright, so first observe that we have 1 here, so it's in the standard form. Also, the degree of the numerator is less than that of the denominator, 1 less than that, right? So this is a strictly proper transfer function. This is a third order transfer function. So A is in the first companion form 0, 1, 0, 0, 0, 1, and then start in this direction and multiply the coefficients by -1. So this is -8, -14, -7. Is 0, 0, 1, and C is simply okay, so we'll start again in this direction. This is 15, 7, and 3. Alright, so this is in the first companion form. For the second companion form, so let's say this is first companion form. For the second companion form, we have a relation between these two systems. So A in the second companion form is the transpose of this matrix. Then B in second companion form is the transpose of C FCF. Similarly, C in the second companion form is transpose of FCF. So let's write the transfer function in the second companion form. This is simply 0, 1, 0, 0, 0, 1, 1, -18, -14, -7. So realize in that, observe that in the first companion form, you can see that this matrix is standard, right? 0, 0, 1. In the second companion form, you have this as a row vector. So C SCF is 0, 0, 1. B is 15, 7, and 3. Alright, so I hope that this was clear to you. If not, you can ask me a question. So let's look at another question. So G of S 2s cubed plus ms squared plus 21s plus 23 upon s cube plus 5s square plus 7s plus 10. Alright, so observe that this is 1 here, so it's in the standard form. Also, we have s cube in the denominator. So it's not strictly proper, but a proper transfer function. Let's note down the coefficients. This is A0, A1, and A2, B0, B1, B2, B3. Alright, so in the first companion form, the A matrix is start from here. Since B is easy to remember, in the first companion form, it is simply 0, 0. And now, since this is a proper transfer function, we have to calculate the entries of C, right? So this is A0, A1, A2. So we already have the coefficients. So this is 23 minus 2 into 10. So 23. Then it's 21 minus 2 into 7. Then we have 10 minus 2 into 4. Which is 370. Okay. Just a second. So let's write down the transfer function in the standard form. This is so you can see that we do not have 1 here. So let's convert this to the standard form. This is S plus 4. Six is 4 plus 5 is. This becomes 0.5 is plus 2 and s cube plus 6s squared plus 5s. Okay, so now we have one here in the standard form, and this is also a strictly proper transfer function. Right? Before we get to the second companion form, let's write down the matrices for the first companion form. So just to write this down so we don't mess it up, this is plus 0, right? Okay, so this becomes 0 minus 5 minus 6. B in the first companion form is 0, 0, 1. Just add B0 and B1. B2 is 0. Alright, and B3 is also 0. So C in the first companion form is simply B0, B1, and B2. Let's check if this is the so it's B0, B1, and B2. Alright. This is in the first companion form. And second companion form, this is simply 0, 1, 0, 0, 0, 1, 0, minus 5, minus 6. 2.50. And in the second companion form, sorry, is 0, 0, 1. Alright, so let's look at another question to convert to first and second companion forms, and then we'll move on to the Jordan. So y(s) over r(s) is 50 times 1 plus s over 5 plus s 1 plus s by 2, 1 plus s by 50. So the question is to find the first companion form. Let's convert it to standard form. This is 10 times 5 plus s, or let's just take it outside. So 50 plus 10s. S over 100, s plus 2, and s plus 50. So this is so let's write this down in the decreasing parts of s. This is 10 to the power 3s plus 5 into 10 to the power 3 over s. We have s squared plus 52s plus 100. We have s cubed plus 52s squared plus 100s. Okay, so this is 1. So it's in the standard form. It's also a strictly proper transfer function. And this is 0 and again 0 is squared. Alright, so let's write this down. A matrix in the first companion form. 0, minus 100 minus 52. B is the standard column vector, column vector 0, 0, 1. And C in the first quantile form is simply 5 into 10 to the power 3 and to the power 3 means. Alright, so let's pause for a second. And if you have any doubts, please go ahead and ask me. Next, we'll move on to the Jordan canonical form. Alright, so let's go ahead. The third topic is numbers. So let's say this was 2.1. So we'll talk about diagonal form and the Jordan order form. So the key concept is in this section is to know about partial fraction expansion. Alright, so this actually helps you get the if there's a transfer function fs equals, let's say, bs over as, which is something constant times the first zero, the second zero, and so on. First pole, the second pole, the end poles. We assume that m is less than n, which means it's a strictly proper transfer function. Then you can always write f of s as some constant c1 over s plus p1, and c2 over s plus p2, so on till cn over s plus pn, where, for example, c1 is fs, this whole ratio times s plus p1 and s equals minus b. And you can calculate the other coefficients too. So in this case, the inverse Laplace transform of this is simply c1 e to the power minus p1t, so on, plus cn e to the power minus p2t. Let's talk about the Jordan normal form. The Jordan normal or the diagonal form. So in this case, the matrix, the A matrix simply looks like lambda 1, lambda 2 till lambda n, zeros everywhere on the off diagonal terms. So this canonical form follows directly from the partial fraction expansion of the transfer function. So lambdas are the eigenvalues or the poles of the transfer function. Eigenvalues of the system or the poles of the transfer function. That is the roots of the denominator polynomial. Alright, so let's look at the diagonal canonical form. For distinct eigenvalues. Say that the transfer function is ys over rs. This is b0 to the power x to the power n plus b1 x to the power minus 1. So the numerator, the subscripts, the coefficients are named such that their subscript plus the power of s equals n, right? And then we have the simplified version of the denominator, s plus p1, s plus p2, s plus pn. So we are talking about distinct eigenvalues. So p1 not equal to pn. And this will be a proper transfer function. If b0 equals 0. So you can write down this transfer function as b0 plus c1 over s plus p1 or c2 over s plus p2 s plus pn. Alright, so we've already discussed on how to compute these coefficients c1 to cn. We already know if b0 is 0 or not. In that case, the system, the state space model in the diagonal form is written as x dot equals minus p1 minus p2 till minus pn. Zeros are everywhere else. X plus b has a special form, so it just has 1. So it's a column vector of dimension 1 by 1. And C. The output y is we'll form it using these coefficients c1 to cn. This is c1, c2, cn x plus b0. So if it's a proper transfer function, then matrix D is 0, right? So this is A, B, and C. D is 0 for proper transfer function. Now let's look at the state space form if there are multiple eigenvalues at the same location in the S. So in that case, we'll have a block diagonal form in the A matrix and we'll see. This is Jordan on canonical form. eigenvalues, the same look. This is ys over rs equals b0 x to the power n b1 plus n minus 1 to bn over. So let's take a specific example. Let's say that the first pole is distributed 3 times. So this is x plus p1 to the power 3. Sorry, this is 3. Then we have x plus p2 and then so on. Right? This can be written as, let's say this is some bn. So this is b0. Now for the first pole, there will be 3 coefficients. So let's name them c11 over s plus p1 cube plus p1 2, sorry, p1 squared plus c13 s plus p1. And since the other eigenvalues do not repeat, this is simply c2 over s plus p2 plus cn over s plus p2. Okay, so if there were multiple poles at the second location, in that case it would be, for example, c21. For example, so there are 2 eigenvalues at p2. This would be x plus p2 squared plus c22 s plus p2, right? And now we have to calculate the coefficients c12, cn, all these. Okay, so in this case, the system matrix A looks like a block diagonal form. That is, each block of the matrix A looks like a diagonal matrix. So this is diagonal matrix with ones on the off diagonal term. So this is minus p1, minus p1, minus. Since we have 3 repeating poles at p1, then 1 above it and 1 here. 0 everywhere else. Then p2 is just, let's say, only these ones. Then minus p3 minus pn. 0s everywhere else. This is going to be a n-by-n matrix. B again is going to be just once on the column vector, and C would depend on the coefficients. This is C1 to Cn, and D is again B0. All right, now let's look at a few questions. So this is question number 8. This is n s plus 4. So s plus 1, s plus 3. So the denominator has already been simplified. This is ns plus 40. S is plus 1, s plus 3. So we have to obtain the diagonal canonical form for the above system. The poles are, or the eigenvalues are at 0, -1, -3. So A is going to look like, so is first of all a 3 by 3 matrix. This is 0, -1, -3. Simply 1, 1, 1. And C, since the eigenvalues are not repeated, is C1, C2, C3. And what about D? So D is 0, right? There's no power of S cubed in the, there's no coefficient for S cubed in the numerator. So now we have to figure out these coefficients C1, C2, and C3. So let's say that this was 10s plus 40, S plus 1, S plus 3. So C1 is going to be 10s plus 40 plus S plus 1, S plus 3 times S at S equals 0. This gets cancelled, which is 40 over 3. Similarly, C2 is, so you just have to remove S plus 1 from the denominator for C2, right? This is equals 10s plus 40 over S plus 3 evaluated at -1. This is minus 10 plus 40, then -1 times 2. This is -2. Alright, similarly, you can compute C3 as 10s plus 40 over S plus 1 evaluated at S equals -3. So this is 10 -3 and -2. This is 5 over 3. Alright. So C looks like this is 40 over 3 minus 15 and 5 over 3. Alright, so I hope that this was clear to you. If you have any doubts, please go ahead and ask. Look at the next question. So G of S is S plus 3 over S cube plus 9s squared plus 24s plus 40. Okay, you have to find the diagonal form. Alright. So first observation is that this is strictly proper. B0 is 0, right? So this means that D would be 0. You already know that B is going to be 1, 1, 1. To find A, we need the eigenvalues or the poles of the system. And to find C, we need those coefficients, right? So let's do the partial fraction expansion. And first, let's simplify the denominator. So if you put S equals -1, then the denominator is is minus 1 plus 9 minus 24 plus 20. Okay, so this is not 0. So s plus 1, we cannot write in the denominator. Let's try s equals minus 2. This is minus 8 plus 36 minus 48 plus 20. This is and then plus 56, right? Yeah. So s plus 2 is a root. So s plus 2, s cube plus 9s squared plus 24 s plus 20. So this is s squared minus plus 7 s. So this is 7s squared and this is simply 10. Okay. So the transfer function g of s is s plus 3, s plus 2 and s squared plus 7s plus 10. Alright, now let's simplify the second term. S is minus v plus minus plus device minus 7 so I have minus 7 minus 3 by 2 minus 7 plus 3 by 2. Okay, so now we have simplified the denominator. This is s plus 2 squared and s plus 5. So we have multiple eigenvalues at s equals minus 2. So A would look like minus 2 minus 2, 1 here and then 0, and then minus 5. This is the block for lambda equals minus 2. And now we need those coefficients, right? So let's compute g of s. So c11 over s plus 2 squared plus c2 over s plus 1. So c2 is easy to tackle, right? c2 is s plus 3, s plus 2 squared at s equals minus 5. So this is simply minus 2, and then minus 3 squared, minus 2 over 9. Okay, now let's see, if we multiply both sides by s plus 2 squared, we get s plus 3 over s plus 5, c11 plus c12 s plus 2 plus c2 s plus 2 squared s plus 5. And then if we substitute s equals minus 2 on both sides, we get, so this goes to 0 and so does this. C11 is 1 over 3. Now observe that we cannot do this for C12, right? So if we multiply by s plus 2 on both sides, this is simply 2. So at s equals minus 2, this goes to 0. This becomes a very large number, and you cannot compute this because s plus 2 tends to 0, right? Alright, so to do this, let's simplify the expression on both sides. This is s plus 3 equals C11 s plus 5, right? If you multiply by this on both sides, multiply by s plus 2 square times s plus 5. Then we have C12 plus C2 s plus 2 square. Okay, so let's expand this. This is C11 s plus 5 plus C12 s square plus 7s plus 10, C2 square plus 4s plus 4. So our s square terms are C12 plus C2 plus s times C11 plus 7C12 plus 4C2 plus 5C11 plus 4C2 plus C2. So just see. Let's check if this is correct. Alright. The next step is to compare the powers of this. Compare the coefficients. So we get C12 plus C2 equals 0, which implies C12 is minus C2, and you already have C2, right? This is 2 by now. Alright. Then from the second equation, it's going to be 5C11 so the only unknown is C11. You can find this out by substituting C12 and C2. This is 1 by 3. So C is 1 by 3, 2 by 9, minus 2 by 9. So I think D is already 0 because you have observed that it's a strictly proper transfer function. Alright. So this is A. This B, D is 0, and this is C. Alright. Now let's look at another question. So the transfer function is, this is question 10. So G of S is S cube plus 8s squared plus 17s plus 8 over s plus 1, which is already simplified, s plus 2, s plus 3. Okay. So first of all, this is not a strictly proper transfer function, it's a proper transfer function because we have non-zero coefficient of s cube. So this is proper transfer function. And also we have distinct eigenvalues or poles. Alright, so in this case, A is simply -1, -2, -3. B is 1, 1, 1. D is B0, which is the coefficient of S cube. This is 1. Now we need to find C. G of S is B0 plus C3 plus 3. And which is equal to S cube Alright, so you can observe that if we cross multiply by the denominator polynomial, this is, this is S cube plus 8S squared plus 17S plus 8. This is B0 times S plus 1, S plus 2, S plus 3 plus C1 times S plus 2, S plus 3 plus C2 times S plus 1, S plus 3 plus C3 times S plus 1, S plus 2. Alright, so observe to find C1 if there was no B0, we simply put S equals -1, right? So we can still do it here because if we substitute S equals -1 or -2 or -3 to find C1, C2 or C3, this would always be 0, right? So let's see CO for finding or for computing C1, C2, C3. So we again have the same formula for computing C1, C2 and C3. C1 is we remove S plus 1 from the denominator and S equals -1. Evaluated at -2. So you can verify the calculations later. This is -1 to 1. So C becomes -1 to 1. Alright. So one thing to observe is that this is when we write A as -1, -2, -3, right? So we have actually chosen that lambda equals -1 is the first hiding value, then -2 and -3. We could also rewrite A as, let's say, -2, -1, -3. And in this case, the corresponding C would be the coefficient for -2, coefficient for -1, and then 3. Just notice. Alright, so another thing to observe from here that, for example, the transfer function is B0 is cubed plus B1 is squared plus B2 plus B3 over S plus B1 till, let's say S plus B2 and S plus B3. So this is a proper transfer function. And if we, as we are discussing, if we want to convert it to a diagonal form or the Jordan form, You should also verify that uh, this does not have a common root as a denominator. For example, if this is s plus b1, let's say s plus z2 and s plus z3, there would be a pole zero calculation, a pole zero cancellation, and we would have this transfer function. So if it's not specified, as we have done in the previous question, you can just go ahead and find the ABCD matrices. So let's pause for a second. We'll move on to the next topic of equivalent state space systems. All right, so since we have already discussed that there is no unique state space representation, so for the same system, we could have x dot equals, let's say, ax plus bu and y equals cx plus du. And let's say the same system can be represented by the state z. This is z dot equals, let's say, a bar z plus b bar u, and the output was c bar z plus d bar u. And since we are talking about the same system, there should always be a transformation between the two states, x and y, right? So this is x, the system is z. So let's assume that the system z can be written as t times x, right? So, but the order of the system remains the same, right? So if x is x1 till xn, z is also a column vector of z1 to zn. So this means that T is going to be a square matrix of size by n. So if it's a square matrix, we can check if the determinant of T is non-zero. This would mean that T is invertible. This means that we could transform into any state, right? So if we know T and X, then we know Z. If we know T inverse and Z, then we know the state X, right? All right. So the relation is Z equals Tx. And if we take the derivative, Z dot equals, and let's assume that T is a constant matrix, right? It does not have time dependent terms. So this is simply Tx dot. And let's substitute x dot. So this is Tax plus Tb. Now, if it's a state space model in Z, so Z dot should have terms in Z, right? So Ta and X is T inverse Z plus Tb. So this means this was the new A bar matrix. This is B bar. Similarly, the output Y, which is Cx plus Du. So X is T inverse Z plus T. This is C bar. and this is data. All right, so I hope that this transformation matrix was clear to you. Now let's move on to state equivalent. State equivalent models. All right. So two models are state equivalent if the characteristic equation and the transfer function are same, right? So when are the characteristic equation same? When the eigenvalues are same, right? So lambda and GS are same. Or you might also have talked, you have discussed about it in the lecture. They should have the same characteristic equation, this and the transfer function. State equivalence is if the two systems have the same transfer function. And we already know how to compute a transfer function from its state space model. Alright, so let's look at a question. Okay, so we have x dot equals the first system is x dot equals 1 0 0 1 x plus 1 0 2 y is 1 0 x. And the second system is, so this is the first system, and the second system is x dot equals 1 0 0 2 x plus 1 0 2 u and y equals 1 0 x. Alright, so let's make a few observations. D is 0 in both cases. And observe that the system matrices A in both the cases are diagonal, right? So let's say this is A, B, C. This is A bar, B bar, C bar. Alright, so eigenvalues of A are 1 and 1. A bar are, sorry, minus 1, minus 1. And minus 1, minus 2. So these are not same. So we don't have to check the transfer function for state equivalence, right? Because the eigenvalues are not same. So the two systems. We have to prove zero state equivalence. We'll have to find the transfer function for both the systems. So let's do that. Let's say G1S is or GS C times SI minus A equals B and G bar is so let's compute this quickly. SI minus A is plus minus 1 This is a 2 by 2 matrix. It's simple to calculate the inverse, right? So it's 1 0. So it's 1 0 in both the cases. For both the systems. This is 1 0. Okay, so this is S minus 1 0. So only the first row. This is again only the first row. S minus 2 0. And then post multiply by B. B is also same 1 0. So that's the first entry of this row vector, right? So C first entry is S minus 2. Okay, so the two transfer functions are the same. The two systems are zero state equivalent. So I hope that this was clear to you. Let's look at another example of equivalence. So this is question 12, and this would be the last question for today. So the two systems are x dot equals 1 0 0 1 x so plus 1 0 u, and the output is y equals 1 0 x. So the first system is a second order system. We have a 2 by 2 system matrix. The other state is x bar. So x bar dot is x bar plus u, and y is x bar. So x bar is a scalar. So now we have to prove equivalence between a second order system and a first order system. So you can observe that this is the same system as in the previous question, and the transfer function was simply 1 over s minus 1, which means that it could be represented by just one state, right? The degree of this is 1. Alright. So you know the transfer function for this one. This is gs 1 upon s minus 1. Okay. Now for this, g bar s is c si minus a bar inverse p. So observe that d is 0 in both the cases, right? So plus d is 0 bar quantities. So this is a bar. A bar is 1, b bar is 1, c bar is 1. Right? And identity matrix in one dimension is just 1. This is 1 times s minus 1 inverse. Okay, so the transfer function are the same. The two systems are so the two systems are zero state equivalent. And what about the eigenvalues? So lambdas are -1, and lambda bar is just -1, right? Or sorry, +1. Alright, so these are two eigenvalues, although they are repeated, and this is just one. So the eigenvalues of the two systems are not the same. Therefore, the two systems are not steady. Alright, so let's pause for a second. This was the last question of today's session. If you have any doubts, please go ahead and ask. If you have no doubts or questions, you are free to leave. The values are fine. Alright, so if there are no more questions, let's end today's meeting. Thank you.